Okay, today we're going to look at three important properties of Laplace transforms. The first one is if you want to calculate the Laplace transform of a function that's in the form t times f of t, and you know the Laplace transform of f of t, then it's very easy to calculate the Laplace transform of tf of t. That's equal by the negative of this transform, and I've written it in this order because that's the order in which you want to look at it if you want to prove it easily. But anyhow, this Laplace transform, the negative of this transform is equal to the derivative with respect to s of the Laplace transform of f of t. And again, it's very easy to write this out and see why it is. That can also be written as negative Laplace transform of t little f of t is equal to the derivative with respect to x of capital F of x s, capital F of s, where capital F of s is the Laplace transform of f of t. Remember, the Laplace transform is a function of s. Okay, now if we write this out in the more usable form, the more commonly used form, we'd have the positive on this and the negative here and here. Still, this is the order in which it's going to be proven, and that's the order in which I chose to write it. Okay, then we have the convolution. There are all kinds of things you can do with convolutions, and I don't know everything you can do with convolutions, but you know, they arise, and they arise throughout mathematics. Okay, way beyond the introductory differential equations course. Anyhow, the convolution says, the convolution theorem says that the transform of a convolution is the product of the transforms. Now, what's a convolution and what transforms are we talking about? Well, here we have the definition of the convolution. F convolution G, I'll read it that way, and I'm using an asterisk with a circle around it. Often the asterisk is used for the notation of a convolution, but the asterisk is also used for multiplication, and we're very familiar with that. We don't want to confuse it. Now I put a circle around the asterisk, which could tend to cause confusion with like the symbol for the direct sum, the plus sign with a circle around it, and most people taking this course have had or are taking a linear algebra course where you see direct sums, so you don't want to get confused with that, or the tensor product or the direct product of well, the tensor product, okay? That would be like a multiplication symbol with a circle around it. We don't want to make that confusion, but with that instead, that's the notation I'm choosing to use. Okay, well anyhow, the convolution of f with g, f convolution g if you wish, is just the integral from 0 to t of f of tau g of t minus tau d tau. Now, we use tau here because we've got a t here, and we want to distinguish the t that we have here, which matches the t that we have on the integral, the limit on the integral, from the variable of integration, which is tau. Okay, so we integrate with respect to tau, we get an antiderivative, and then we substitute t, and of course we substitute 0. Typically we'll get some t's out of the g of t function. That'll be the same as the t's that we have here. Now it turns out that it doesn't matter in which order you do the convolution. If instead you do g of t f of t minus tau rather than f of t g of t minus tau, it's going to be the same. And that's really kind of important because in many applications we need to make the appropriate choice of which way to do this. Okay, the convolution theorem then says what I said here, but let's see. It says Laplace transform of f convolution g is the Laplace transform of f multiplied by the Laplace transform of g. Okay. Now you might think that the Laplace transform just f multiplied by g ought to be the Laplace transform of f multiplied by the Laplace transform of g, but that doesn't happen. just like you have all kinds of illusions of linearity, like you think that f of a plus b should equal f of a plus f of b. Hopefully we've passed that a long time ago. Similarly, you might think that this ought to work for just plain multiplication, but it doesn't, and you can come up with all kinds of counterexamples. You've already seen many. Okay, so anyhow, there's the convolution, and we'll talk about different ways you can apply it after we get a little more familiar with it. Periodic function. A periodic function, well, the sine function is a function that's defined from 0 to infinity, and it's periodic. It has a period of 2 pi. That means that in the case of the sine or the cosine function, as far as that goes, f of t plus 2 pi equals f of t. That is, you got the graph, you know, the y-coordinate of the graph. If you have a certain t here, and you get a y-coordinate from that value of t, if you move 2 pi units, you're going to be at the same place in the cycle of the sine function, and you're going to get the same y value. So f of t plus capital T equals f of t, where capital T is the period of the function. That's the basic definition of a periodic function. And make sure you review that if you're not real familiar with it. Okay. If the function is periodic, then it turns out that you can calculate its Laplace transform by simply doing the Laplace transform integral, but only from 0 to capital T. That is, only through one period. If you can integrate the thing over one period, then you have the Laplace transform, because the Laplace transform is just that one period integral divided by 1 minus e to the negative s capital T. It's very easy to derive this. Now, there are actually two ways to derive it. There's a slick way, which has its share of insight, and then there's the way that you can do it that gives you a little more insight into the graphical nature that involves the sum of geometric series. Okay, sometimes the words aren't there. It is allergy season. I do apologize for that pause. Okay, so there we have it. So that's the program, and we're going to look at these properties and some of their applications.